We open in the middle of the story. A small ball sits on a gently curving surface, and it is already moving, easing downward along the slope. Before it takes each step, it pauses, as if feeling the ground beneath its feet to decide which way is downhill. That single instinct, feel the slope then step downhill, is the whole idea behind gradient descent. It is the quiet engine humming underneath nearly every modern neural network. Today we are going to build it up from almost nothing. To make this concrete, we need to know what that curved surface actually represents. In machine learning, it is called a loss surface. Its height at any point tells you how wrong your model currently is. High up means very wrong. Down in the valley means much better. So training a model is really just one goal in disguise: find the lowest point on this surface. Everything else is technique. Let us strip the picture down to the simplest possible case. Forget billions of settings for now. Imagine your entire model has just one knob to tune, one single number to choose. With one knob, the loss becomes a simple curve, a parabola, a bowl seen from the side. Each horizontal position is a possible value of the knob, and the height of the curve above it is how much error that choice produces. We start the knob at some random value, so our dot lands somewhere up on the side of the bowl. We do not yet know where the bottom is. All we can do is look at the ground right where we are standing. Here is the crucial move. Even without seeing the whole curve, you can measure how steep it is at your exact spot. Lay a tiny straight ruler against the curve where you stand, and it tells you which way tilts down and how sharply. That tilt is the slope, and in calculus it has a name, the derivative. The derivative at a point is simply the slope of that little tangent line. It is a single number that captures the steepness under your feet. The sign of that number is what matters most. On the right side of the bowl, the curve goes uphill to the right, so the slope is positive. On the left side, it goes uphill to the left, so the slope is negative. Notice the beautiful symmetry. Downhill is always the opposite direction of the slope. If the slope points up to the right, downhill is to the left, and vice versa. So to move toward the bottom, we step against the slope. This gives us our update rule in words. Take your current knob value and nudge it in the direction opposite the slope. Do a little of that over and over, and you drift steadily toward the minimum. Now let us write it a little more precisely because we will need it later. Call the knob x. The update is, the new x equals the old x minus a learning rate times the slope at x. Let us unpack every piece. The slope tells us which way and how steeply the ground falls. The minus sign flips us from uphill to downhill, and the learning rate is a small positive number that controls how big a step we dare to take. Watch what the minus sign does automatically. On the right side, the slope is positive, so minus the slope moves x to the left, toward the valley. On the left side, the slope is negative, so minus a negative pushes x to the right. Either way, we head down. There is another elegant feature hiding here. The steeper the slope, the bigger the step. Far up the wall of the bowl, the ground is steep, so we take large strides. Near the bottom, it flattens out, so our steps naturally shrink. Let us actually run it. We start high on the right, measure the slope, take a step, measure again, step again. Each move is a fresh arrow, and each arrow is shorter than the last as the ground levels off. This shrinking is exactly what we want. It means the process slows down and settles gently as it approaches the answer, rather than crashing past it. The dot glides in and comes to rest almost exactly at the minimum. Pause and appreciate what we have. With only local information, the slope under our feet, we found the lowest point of a curve we never saw all at once. No map, no overview, just repeated small honest steps downhill. But real models never have just one knob. They have thousands, millions, even billions. So we need to see how this idea survives when the surface has more than one dimension. Let us add exactly one more knob and watch. With two knobs, the lost surface is no longer a curve but a bowl, a genuine three-dimensional valley. The floor is our plane of possible settings, and the height above each point is still the loss how wrong that pair of choices is. The goal has not changed one bit. We still want the lowest point, the bottom of the bowl, and we still refuse to look at the whole thing at once. We only get to feel the ground right where the ball sits. Standing on a 2D surface, though, there is a new subtlety. There are infinitely many directions you could step: forward, sideways, diagonally. Each direction has its own steepness, so which way is truly downhill? To answer that cleanly, let us flatten the bowl into a map, seen from directly above. This is a contour plot, exactly like the elevation lines on a hiking map. Each ring joins points of equal height on the surface. Reading these rings is a skill worth pausing on. Where the rings are packed tightly together, the surface is steep, height changes fast over a short distance. Where the rings are spread far apart, the ground is nearly flat. Now place our ball as a dot somewhere out on the map, away from the center. It sits on one particular contour ring. Downhill means crossing toward the inner rings, toward the center where the loss is lowest. Among all the directions you could step, one is the steepest descent, the direction that drops your height the fastest. That single best direction has a name. It is closely tied to something called the gradient. The gradient is just the two-dimensional cousin of the slope. In one dimension, the slope was a single number. Here, the gradient bundles together the steepness in the first knob's direction and the steepness in the second knob's direction into one arrow. And here is the key fact. The gradient arrow points in the direction of steepest ascent, straight uphill, the fastest way to increase the loss, which means the fastest way down is simply the exact opposite, the negative gradient. There is a lovely geometric bonus. The steepest direction is always perpendicular to the contour ring you are standing on. Downhill cuts straight across the rings, at right angles, never along them. So our update rule barely changes. Take your current pair of knob values and step in the direction of the negative gradient scaled by the learning rate. Same recipe as before, now just following an arrow instead of a single number. Let us run the full descent on the map. Step by step, the dot marches inward, each move perpendicular to the ring it is leaving, tracing a path toward the center where the loss bottoms out. But look closely at the shape of that path. If the bowl is stretched, like a long, narrow valley rather than a round one, the descent does not go straight in. It zigzags, bouncing from one wall to the other as it inches forward. That zigzag happens because steepest descent always points across the nearest wall, not toward the far-off bottom. In a lopsided valley, the quickest local direction and the true destination disagree, so the path oscillates as it corrects. It still gets there, just less directly. This brings us to the one dial we have quietly been ignoring, the learning rate. We called it the step size. It turns out this single number can make or break the entire process, so let us study it carefully. First, imagine the learning rate is far too small. Every step is a timid shuffle. The dot does move in the right direction, downhill, but it barely budges, taking hundreds of tiny steps to make any real progress. It gets there eventually, but eventually can mean an enormous amount of computation. For a billion-parameter model, a learning rate this small could mean the difference between training in hours and training in years. Now swing to the opposite extreme, a learning rate that is far too big. Each step overshoots the bottom entirely, flinging the dot up the far wall, higher than where it started. The next step overshoots again, even worse. Instead of settling into the valley, the dot climbs out of it. The loss grows without bound, the numbers blow up, and the training diverges. A learning rate too large does not just slow you down, it destroys the whole run. Between crawling and exploding lies the sweet spot. A learning rate that is just right takes confident strides when the slope is steep, then eases in smoothly as the ground flattens, converging in only a handful of steps. Finding that sweet spot is one of the central crafts of training neural networks. There is no single magic value. It depends on the shape of the surface, and much of the practical art of deep learning is learning to tune it well. So far, every surface we have drawn had a single clean bottom. A parabola, a round bowl, a narrow valley, all with one lowest point. But the lost surfaces of real models are nothing like that. They are wild, rugged landscapes. Such a landscape has many valleys, not just one. There is the deepest valley of all, the global minimum, the very best possible setting. But there are also smaller dips, local minima, valleys that are low but not the lowest. Here is the honest trouble with follow the slope. If the ball rolls into a local dip, the ground rises in every direction around it. The slope says stop, you are at a bottom. even though a far deeper valley lies just over the next ridge. Gradient descent is fundamentally local. It only ever knows the ground right under its feet. It cannot see over the ridge, so it can happily settle for good enough while the truly best answer stays hidden behind the hills. You might expect this to be a fatal flaw. In a billion-dimensional world, surely the algorithm gets trapped in bad little dips all the time. And yet, in practice, deep learning works astonishingly well. Why? Part of the answer is that high-dimensional landscapes are stranger and friendlier than our little bumpy picture suggests. With millions of directions to escape in, a point that is a trap in every single direction at once is extraordinarily rare. And crucially, most local minima that do exist turn out to be nearly as good as the global one. In the vast spaces where real networks live, good enough valleys are almost everywhere, so settling into one usually gives a model that works beautifully. There are also clever refinements to the basic loop, momentum that lets the ball roll through small bumps, and randomness that shakes it loose from shallow traps. But every one of them is still built on the same beating heart. Measure the slope, step downhill, now zoom all the way out. A modern neural network is not two knobs, it is billions. Its lost surface lives in a space with billions of dimensions far beyond anything we can picture. And yet the recipe never changes. At every training step, the network computes the gradient across all billion parameters at once, one giant arrow pointing uphill in that unimaginable space. Then it takes the negative and nudges every parameter a little bit downhill. Repeat that nudge millions of times, feeding in example after example, and the loss steadily falls. Slowly, the network's billion numbers arrange themselves into a configuration that recognizes faces, translates languages, or writes text. That is the quiet marvel. The intelligence in these enormous models is not hand-designed. It is discovered one downhill step at a time by the very same rule we drew on a humble parabola. Feel the slope, step against it, repeat. So the next time you hear that a model has billions of parameters, picture that patient little ball pausing to measure the ground before every step, tirelessly rolling downhill. That simple loop, repeated at unthinkable scale, is the engine under all of deep learning. If this made it click, subscribe for more visual math.